Dead men do tell tales. An example of an exponential model. Here's a model of a digital story using the exponential model beginning with this scenario. An NJCU EdTech instructor was found dead one morning in the department computer room. Students wondered if they still had to complete the day's assignments. The police were called, and at 9 a.m. they found the body temperature was 80 degrees. An hour later the body temperature was 72 degrees. Assume the body temperature was 98 degrees at the time of death. Let's ignore the 0.6. And the room temperature was a constant 68 degrees. It's probably with some air conditioning. What was the approximate time of death? So by searching the internet, we found there's a Newton's law of cooling done by Isaac Newton, which fits this model. So for step one, let's review the exponential model. Newton's law of cooling says, if a body is immersed where the surrounding temperature is C, then the body's temperature, capital T, at time t is capital T equals C plus capital T sub 0 minus C times e to the minus kt, where capital T sub 0 is the body temperature at time t equals 0, E is the exponential constant 2.718, and K is a constant that we need to solve for. For step two, let's identify the values from the problem that we're going to use. We said the surrounding temperature of the room was 68 degrees. We said the body's temperature at the time of death was 98 degrees. And then we measured the body 2 times later, but the police measured it. The first time was 80 degrees at some unknown time t. And then an hour later, t plus 1, the body temperature is 72 degrees. Step 3, let's set up the exponential equations. This is the Newton's law of cooling model. T is going to be the number of hours since death. So the first time we measured it, capital T was 80. C is the room temperature of 68. Capital T sub 0 is the 98 at the time of death. C is 68 again, times e to the minus kt. That's equation 1. And then the second time we measured the body's temperature, it was 72 degrees for capital T. The remaining values are the same, but note that the exponent has increased by 1 because it's an hour later. So now we need to solve equations 1 and 2. So step 4 is going to be solving for K. But as a preliminary step, first we need to put the e to the minus kt and the e to the minus kt plus 1 each on the left side of an equation by itself. So in that first equation, e to the minus kt, putting all the numbers on the right side, we get 80 minus 68 over 98 minus 68 is 0.4. For the second equation, we get 72 minus 68 over 98 minus 68 is 0.1333. These are from equations 1 and 2. Now we're going to use equations 3 and 4. Note that if we take equation 4 divided by equation 3, on the left side we have e to the minus kt plus 1 over e to the minus kt. We have 0.133 over 0.4, that's 0.33325. By the laws of exponents, this reduces to e to the minus k, which is 0.333. And then if we take natural logs of both sides, the natural log of e to the minus k equals the natural log of 0.33325. Using a calculator for this, we get negative 1.09886. And ln e to the minus k is minus k, so we have minus k equals minus this expression, k equals 1.09886. Now that we know what k is, we can solve for t in the time of death. We had e to the minus kt is 0.4. We now know what k is, so we have this equation. Taking the natural logs of both sides, the natural log of e to the minus 109,886t equals the natural log of 0.4. Using our calculator, we get the natural log of 0.4 is negative 91629. Ln e to something equals that something, so now we have minus 1.09886. T equals 0.91629. Solving for t, we get t equals 0.83386. Now this is the number of hours from 9 a.m. when the first measurement was made. If we convert that to minutes by multiplying by 60, we get 50 minutes rounded. So the time of death is 50 minutes away from 9 a.m., which is 8:10 a.m. And that tells us the time of death was 8:10 a.m. So we used an exponential equation to solve this problem.